So what we will start with, people, is a simple 2D collision where there is a ball that is going to hit a floor and it is going to rebound, and the only thing that is going to be different here than the case before is that the ball is going to hit the floor at a certain angle of incidence. So maybe there is a floor and the floor is here somewhere. This green line is the floor and there is a normal somewhere, of course. So let me also show you where the normal is. So this red line is probably the normal, and there is a ball that comes from the left hand side somewhere. So let me show you the velocity of this ball using the wine red line, initial velocity. So maybe the ball comes in like that, so the ball is initially here like this, and it has a mass m, and it is traveling with a velocity v shown like that, and it hits the floor at a certain angle theta. So usually when they say that it hits the floor at an angle theta, they want to say that the angle of incidence here is theta, and the angle of incidence has the same meaning as it has in ray optics, which you have studied earlier. So this angle here is theta, people. And after the ball hits the floor here, it will rebound, and we have been given probably the coefficient of restitution between the floor and the ball for the collision, and we have to figure out what is the speed of the ball after it rebounds and what is the angle that it makes with the normal after it rebounds. So let me probably take this blue line to show you how can the ball go after the collision. In fact, that will be a very short line because that will be the velocity of ball immediately after the collision only. So that is this, and afterwards the ball will take some kind of a path in an environment that has got gravity in it. So we need to figure out what is its final velocity, and we need to figure out this angle alpha here. And we will have to make a very important assumption here about the nature of the floor and the ball. We will say that they are frictionless. Now the reason we want this assumption to be there is because we don't want any force acting between the ball and the floor along the tangential direction or along the floor. So how do we start analyzing this situation? Let us start analyzing this situation by looking at what are the forces acting on the ball and the floor during the collision, and that will help us gain some kind of insight into what happens. So maybe if you draw the floor here, if you were to draw a floor here and the ball somewhere here, then during the collision there will definitely be a normal force on the ball. So let's start out by drawing the forces on the ball. There is going to be a normal force on the ball. There is going to be balls on weight, mg, acting in the downward direction. So there is n, there is mg, and if the surface was rough, you see that the ball is trying to slide to the right hand side. The ball has got two velocity components, one is to the right and one is downward into the floor, that is just before the collision, and during the collision also it has got that inward component for a certain amount of time. Then the inward velocity component becomes 0, and then there is an outward velocity component for the ball, and there is some kind of deformation that happens here that lasts for a small amount of time, and when the deformation is finally gone, the ball bounces up and it loses contact with the floor, So during this entire time, the ball has got a velocity component to the right. If the ball has got a velocity component to the right, then friction will be acting in the leftward direction. So if there is a rough surface, then there will be friction in the leftward direction as signified by the green arrow here, but then we will ignore this friction for the time being. But you should know that there will be friction, and that frictional force will be mu k times the normal force, because it will be kinetic friction between the ball and the floor, and we will have to take into account that force and the impulse because of that if we have to find out the change in x-axis velocity also. But for the time being, because f is ignored, let us throw this guy off. We don't have the force of friction anymore, and we only have n and we only have mg, and this n here will be an impulsive force. Impulsive because the impact will last for only a very small amount of time. The ball will be in contact with the floor for a very small amount of time, and during that small amount of time it will suffer a finite change in its momentum along the normal axis, which is normal to the floor here, and that can be affected only by either this N or by mg. Now mg is a fixed force. Forces that are constant in value cannot be impulsive, so N has to be impulsive. N will be impulsive, it will be a very large value for a very small amount of time, and so if at all friction exists, that friction will also be a very large value for a very small amount of time. Okay, so this is the force analysis. Now because the floor and the ball are both smooth, therefore we can ignore this force of friction. And now what we have to do is, because we have a force acting only along the normal axis, let me take a pair of axes to start with. Let me say that there is a normal axis which is perpendicular to the surface, perpendicular to the floor, and there is a tangential axis T which is along the tangent to the surface like this. And I can then claim that since F external on the ball along the tangential axis is 0, therefore velocity of ball along the tangential axis is a constant. It will not undergo any change. Okay, so that's one thing. Second thing is that because everything about the collision is only along the normal axis, a change in momentum occurs along the normal axis. In fact, I will have to use the coefficient of restitution also only for the normal axis. For that reason, I can treat this entire process as a one-dimensional collision along the normal axis. And the moment I say 1D collision along the normal axis, you know what has to be done. So we can safely go ahead along that route. Now, if I were to draw the velocities of this ball just before the collision, you will see that there is V at an angle. So this is V, and the way in which we have chosen the angles, this angle would become theta with the vertical here, because if this angle is theta, then this angle here will also become theta. So you've got theta and theta. This velocity here, the vertical component towards the floor, is going to be V cos theta, and the component towards the right, which is the t-axis, is going to be V sin theta. And you will see that the ball is approaching the floor with a velocity V cos theta. So therefore I can claim that the speed of approach here, speed of approach, is going to be V cos theta. And this entire diagram is before the collision, just before the collision. So let me also mention that here, just before. Now what happens just after the collision? Now just after the collision, we will have the ball going at some angle, let's say alpha with the vertical, with some speed, and let's call that speed V0 or something, and the vertical component will be V0 cos alpha and the one along the tangential axis will be V0 sin alpha. And then you know that the ball is going to go away from the floor because of V0 cos alpha. So I can say that the speed of separation is going to be V0 cos alpha. And here we can make a mention of that. Speed of separation will be V0 cos alpha. And then if I want to use E, I will have to use E along the normal axis, and one of the equations that I can frame is E is equal to V0 cos alpha divided by V cos theta. It implies that V0 cos alpha is EV cos theta, and this will be, let's say, our equation number 1. What else? We know that along the horizontal axis there was no force acting on the ball. We have said that, F external along the tangential axis on the ball is 0, so therefore the velocity of ball along the tangential axis should be a constant. So therefore v sine theta should be equal to v naught sine alpha. So we have got that also. So equation number 2 will be simply v naught sine alpha is equal to v sine theta. This is equation number 2. And 1 and 2 give us a way of finding out v naught as well as alpha. So if you square and add, squaring and adding 1 and 2, you will get v naught square cos squared alpha here, v naught squared sine squared alpha. You take v naught squared common, and cos squared alpha plus sine squared alpha is 1. So v naught square is equal to, you will get v naught squared is equal to, on the right hand side you will have e square v square cos square theta and v square sine square theta. So v square can be taken out. You will have v square and you will have e square cos square theta plus sine square theta, and so therefore v naught will be v times root of e squared cos squared theta plus sine squared theta. So you have done this, not a big deal, and let us box that result. Now how about this angle alpha? So this angle alpha can be found out merely by taking a ratio of equation 2 to equation 1, which means LHS of 2 by LHS of 1 by RHS is equal to RHS of 2 by RHS of 1. So you do a 2 divided by 1 and you will end up with tan alpha is equal to E times, sorry, not E times, you will have tan theta times tan theta by E. So this is the equation that you are going to get if you have 2 divided by 1, and we know that since E is going to be less than or equal to 1, in fact, okay, let's have the equality anyways. So because E is going to be less than or equal to 1, therefore tan alpha is going to be greater than or equal to tan theta, signifying that alpha is greater than or equal to theta, because we are in the domain 0 degrees to 90 degrees. If alpha and theta both belong to the set of all angles between 0 degrees and 90 degrees. In fact, I should not have square brackets, I should have parentheses to show that these two endpoints are not included. At 90 degrees, it will simply be infinite, the value of tan will be infinite, and at 0 degrees again it will be a normal collision. So the ball will come and hit the floor perpendicularly if theta is 0 and will bounce off perpendicularly, so that's one. And if theta is 90, then this ball will come sliding along the floor and nothing significant will happen because the ball and the floor both are smooth. So we are going to exclude those angles, but other than that, if I look at any other angle within this range, if tan of alpha is more than tan of theta, then alpha is more than theta. That means I expect this ball to have an angle of incidence theta that is lesser than the angle of reflection alpha. So the laws of reflection do not exactly hold. But then there is a special case in which the laws of reflection will hold. And what if there is a perfectly elastic collision? So for a perfectly elastic collision, what are we going to get? Since E is 1, therefore we can say that tan of alpha will be equal to tan of theta. Tan of alpha is equal to tan of theta. It implies that alpha is equal to theta. So angle of incidence is equal to angle of reflection. That's number 1. And when you insert the value of E is equal to 1 here in the speed equation, you will get cos square theta plus sine square theta, which is a 1. So V naught will be equal to V. And V naught is equal to V. So the usual laws of reflection that we know, they work only for a perfectly elastic collision, otherwise not. So this is how you should deal with a case of a ball hitting a wall. And if you were to figure out the change in momentum, suppose they ask you to find out the change in momentum of this entire ball, then in vector notation finding change in momentum, that's actually pretty simple. We can take the ball and draw its initial velocity. There is this ball coming in with a velocity v, which has two components. There is v sine theta along the x-axis or the tangential axis, and v cos theta along the normal axis here. And on the way back after the rebound, it has got ev cos theta away from the floor, and still it has got v sine theta towards the right. So you can take the usual coordinate axes. You can take x-axis to the right, and you can take y-axis upwards, or maybe if you want to work with the normal and the tangential axes, the one to the right will become tangential in this case, the one on the top will be normal, and you will say that the initial velocity was v sine theta along tangential axis minus v cos theta along the normal axis, and velocity final will be v sine theta along the tangential axis plus ev cos theta along the normal axis. So therefore change in velocity is you see that you will have v final minus v initial, so the first term will cancel out, and the second term here will get added up to the ev cos theta term here. You can take v cos theta common, v cos theta times e plus 1 n cap, and so therefore delta p is going to be mv cos theta times 1 plus e in the n cap direction. Because the value of E is 0, since E is 0, therefore the speed at which the ball rebounds is going to be 0. V naught cos alpha is going to be 0. Or let me not even say that, let me just say that velocity of separation is going to be 0. And in this case what will happen is, before the collision the ball looks like this here, where it was coming in with a speed v, horizontal component v sine theta, that's along the tangential axis, v cos theta along the normal axis, and after the collision the ball will become something like this, going towards the right with v sine theta, but there is no velocity of rebound. So in fact this velocity, which I have marked with the question mark here, is in fact 0. So it keeps on going along the floor. Now if the floor had friction and if it was a spherical ball, let us say, then after some time there may be pure rolling, but right now it is only sliding. And we will have a look at the difference between these two in a later class, perhaps when we are dealing about the rigid bodies. But just to give you an idea, when this ball slides, the relative orientation of any point on this ball with respect to the floor does not change. So maybe if I just draw this ball here with some points marked on it, let us say you have A at the bottom and B on the left hand side, C on the top, and then so on. As this ball slides, the same orientation will be there at any later time, and this will be true only if the floor is frictionless. So this same orientation will keep on going for as long as the ball keeps on only sliding. So for that matter, this ball could have been just a lump of clay or something, and then you could have thrown this lump of clay onto the floor at a certain angle with the vertical, and then as that ball of clay hits the floor, it won't rebound because it's perfectly plastic, but then it will keep on sliding if there is no friction, and that is what will happen. So there will be a certain deformation here that the ball would have suffered, and that will never ever be recovered. So there will be a large loss of energy, in fact the maximum loss of energy in any kind of collision. And we can also evaluate that loss of energy, because we know that initial kinetic energy coming in was half mv square. Now it's half mv square sine square theta, so we know that the maximum loss in kinetic energy will be half mv square cos square theta, right? So we can find that out also. And this ball will keep on sliding along the floor. If there is friction, then they can ask you to solve a problem where it also rolls after some time. So you may have to find out the time after which it rolls, or the final speed of the ball when it starts rolling or something. That's a different thing.